Last time we learned how to sketch Bode plots for constants, which just have constant Bode plots of magnitude and phase. We learned how to sketch them for poles and zeros at the origin, which were just straight lines as well. So backing up a little bit here. And then, so these were the poles and zeros at the origin. And then here there's the real pole and zero transfer functions. We learned how to sketch those. And it all depends on the break frequency, right? That's like the key thing, was the break frequency. And then we learned about how to sketch a second order conjugate pole pair and conjugate zero pair. We learned about that as well. We learned all of those. And what I said at the beginning of all that is, if we learn all of those, we're going to be able to rewrite our higher order transfer functions as products of these types of systems. So constants, poles and zeros at the origin, first order systems and second order systems. So those are the possibilities. We can essentially factor it out into those anytime we want. It might take a little bit of work, but we can do it. So if that's the case, then we can sketch higher order ones as well, using this nice little aspect, which we already learned about, but I wanted to review here at the end. So we can use MATLAB's Bode command to create Bode plots. However, we must understand how these plots relate to their transfer functions. In this section, we learn to sketch Bode plots in order to deepen our intuition of this relationship. So let's say that we wrote our transfer function as a product of several lower order transfer functions, okay? So that's what this big capital pi means, this product. Just like big capital sigma means sum, this means product. And then let h of s be the product of several factors. So then the magnitude and phase are just going to be the product of the magnitudes, right? And the phase is going to be the sum of the phases. Okay? So that's all sort of review. We knew that was the case. We kind of reviewed this right before. The Bode plot consists of plots of 20 log base 10 times magnitude of, or not times, so log base 10 of the magnitude of h of s, and the phase with s going to j omega. The magnitude and phase expressions become, so what's nice is, so the phase is already a sum, right? We want a sum, and it's already a sum, so we're good. If we take the dB version of the magnitude, it ends up summing too. Remember, it's a log property, so that's convenient. Now we can sum the dB magnitude plots, and we can sum the phase plots as well. And that's what we're going to do. So this result means we can graphically sum both the magnitude and phase Bode plots of the individual factors of the transfer function, as long as we are adding magnitudes in dB. So as long as we do the magnitude in dB, we can just add them together. Okay, so now we've got all the tools in our tool belt. Let's apply them to the good old vibration example that we did before. I mixed in a little bit of design into this problem for fun, because as much as we like analysis, we love analysis in this class, we like to design with these things eventually. And so I'm going to help us think about how we might choose the spring and the damping coefficient. So remember, this is a motor mount that we're doing the vibration example on. So we have a motor mount, and we're trying to design the spring constant K and the damping ratio B of that motor mount such that it behaves in a certain way, okay? So that's a real engineering problem you might have to do, and so we're going to design for that. We have the transfer function from part 1, right? This was the amount of force that gets transmitted through the mount to the chassis. And we got this expression. So we want to design by selecting K and B, and what we want is a damped natural frequency, omega d, of 20 radians per second. So that is something that we chose based on probably the idea that our motor is going to be operating at a much higher frequency than that. And we don't want our natural frequency, or our damped natural frequency, which is close to the natural frequency, to be anywhere near where that motor is going to be operating, right? We don't want that. We saw those Bode plots for second order systems that have those resonances at the natural frequency, right? We don't want to be at that natural frequency, because that means that the output amplitude is, how is it related to the input amplitude for being on or near resonance? The output amplitude is greater or less than? Greater than the input amplitude. So we don't want to operate there. We're not trying to transmit this force. We're trying to knock it down, right? So we're going to want to operate in the regime. So this is, notice, it's a second order transfer function. So we're going to want to be, it's going to have a Bode plot that's going to look something like, there is also a 0. So it's not exactly like this, but it's going to look a little bit like one of these plots, right? So we want to have our operating region for our motor to be out here, where there's a lot of attenuation between the input and the output. We don't want to, if we operate at really low frequency, notice it would be, the force would just be the same. So very slowly, it's just going to be the same. And the motor, of course, is going to have to speed up. So it's going to go through this resonance to get there. But as long as it does so relatively quickly, it's probably not a big deal. If it hangs out there, that's when the problem starts. So I want to operate at higher RPMs than where our resonance shows up. And you can't avoid having a resonance. You can't just say, well, I just prefer not to have one. Because anytime you put a motor mount in there, it's going to behave a little bit spring-like and a little bit damper-like. So you're going to have a second order sort of system, or higher. Okay, so that's what we're working with. So we need to select K and B so that we get that natural frequency, or that damped natural frequency, down to a lowish frequency, like 20 radians per second. And we want a damping ratio of 0.2, which damping ratio of 0.2 means that it's not super damped, right? It allows it to sort of oscillate a little bit. And that's like those are our 2 requirements. We get more in depth later on as far as what our requirements will be for design. When we get to the controls part, we're going to get into a lot of that. So something to look forward to. Draw a pole zero plot and a Bode plot of H. So we're going to do both. Okay? So step 1 is the design. So from the standard form of the denominator of a second order transfer function. So this is the denominator of our second order transfer function. Do you remember what the standard form of it is?
You mean like with the damping and stuff?
Yeah. It's s squared plus what? Sounds like we might need to, remember that. Yeah. So we know that omega n squared has to equal k over m, right?
We choosing the denominator because that gives us, this what the second squared is. Like, why not choose the numerator?
Oh, so.
I mean, obviously numerator isn't in the formula, but I mean, like.
So when we are talking about the transient response of these systems, what dominates the transient response of these systems typically are the poles, is the denominator. So remember that poles are equivalent to the eigenvalues, which are equivalent to the roots of the characteristic equation, and these things sort of dominate the dynamics. So the zeros matter, but they're not as important as the poles, and the denominator of the transfer function has this form. You can actually do that for a numerator too, but we often are thinking about the second order system dynamics in terms of this being the denominator. Okay.
So the poles dominate the transient response?
They dominate the transient response, yeah. So if you remember all of the, so your homogeneous solution is always a sum of, hopefully decaying if it's a stable system, decaying exponentials, and the decay rate of each of those exponentials is the pole, right? Is the root of your characteristic equation or your eigenvalue. So those are dominant in what happens. So and the homogeneous response is what's dominant in what happens with the initial condition response. So that's the way to think about it, I guess. Make sense?
Yeah, kind of.
Okay. So we have this. Just by definition, omega n squared has to be equal to k over m. And we have another equation that 2 zeta omega n must be equal to what?
B over n.
B over m. This term. Very good. Recall from the definition of a damped natural frequency.
Square root of something minus 1.
Yeah, so it's omega n scaled by this 1 minus zeta squared. The square root of 1 minus zeta squared. So that's the definition of the damped natural frequency. And zeta here is going to vary from 0 to 1. And we're just going to be essentially multiplying omega n by some fraction of 1, right? So those are 3 equations that we have just essentially from definitions of what natural frequency is, what the damped natural frequency is, what the damping ratio is, right? And 3 expressions. We know zeta. Zeta is one of our design requirements, is for zeta to be equal to a specific value of 0.2. And we know omega d, which has to be 20. How many unknowns are in this? We have also been given, I didn't state it above, but we have 1,000 kilograms for the mass, okay? So that's just given. We can't change the motor mass. I mean, we could probably add mass to it if we wanted to, but when you're designing a motor mount, typically you don't want to have to tell the person, oh, and by the way, you have to add a bunch of weight to your motor when you mount it, okay? That's not really a preferred way to do it. So we say that the mass is whatever the motor is, and we're not going to change that. So we're trying to find what K and M have to be. So we have 3 equations here, and M is known, omega d is known, zeta is known. How many other parameters do we have? We have K, we have B, which we are trying to solve for. What's the other unknown in here? Omega n. We don't know omega n either. So we substitute it. Well, we just can solve 3 equations simultaneously. Pretty easy, actually, to solve them. It's not. It's actually, they're decoupled pretty easily. Like, so you don't have to do a lot of work. And then they're all linear too. Because actually no, they're not. Because omega n is squared. Non-linear. You guys could do it though. I believe in you. So this is the result for omega n. Okay. Poles of the transfer function. So we're going to find the pole 0 plot. So so what did we learn when we solved for omega n, k, and b? We're meeting our design requirements by selecting our k to be this and our b to be this, right? We found out that our natural frequency is 20.4 radians per second, which is just like came along for free. We got that as well. We didn't need to find that, but it's nice to know what the natural frequency is, although we knew it was going to be close to the damp natural frequency. 20.4 is pretty close to 20. So the pole 0 plot. Poles of the transfer function are, so we just take the denominator. I just did it in standard form. I just used the zeta omega n definitions because we have zeta and omega n. Thought I would just do this out. And I solved just using the quadratic formula. And I solved and found that this is the pole location. Okay? These are the pole locations. And if you plug in the numbers, which I did, believe it or not, it's negative 4.08 minus plus J20. So that's where our poles are. Our zeros come from the numerator of the transfer function, right? So we set the numerator of the transfer function equal to 0, and I'm going to define the parameter ta to be b over k, which if you rearrange this to be in a standard first order representation where you have some time constant times s, or in this case z for the 0, plus 1 equals 0, then you get ta equals b over k. So if you solve for the 0, then where should the 0 be? Zero is equal to, solving this for z. I think we can do it. Yeah. Great. So negative 1 over ta, and we know that's equal to negative k over b, just plugging in the definition of ta. And if we plug in those, we found those in the first part, right? We found what those values are. Negative 51.0. And we could also compute what ta is just for fun, which, we will use it to, oops, not omega. I don't know why I wrote that. Ta is equal to 0.0196 seconds. So, pretty fast. So so now we got to plot our poles and zeros. So we have 2 poles and 1 0. We have to put on this plot. Now, the 0 is easy because it's all real, right? It's at negative 51. So we'll put the 0 out here at negative 51. And I'd prefer a different color for that. Ooh, gray. Yeah, I think gray. Negative 51. And thank you. And our poles are going to be, where are the poles going to be? I wrote this so.
It's going to be shifted over to negative finally, and then it's going to be up 20 and then down.
Right, so I don't know exactly where, but somewhere like here, right? Pole here and a pole here. So I might label like this as being 20 or something. All right, that's our pole 0 plot. So I can could label these with like here is P2, here is P1, and here is 0, Z. I love purple and green together. I think they're really nice. They're complementary. Okay. So we have our pole 0 plot. Now we're going to do our Bode plot. Let's write the transfer function as the product of 3 transfer functions. So let's take this guy and let's say, okay, our standard form for a complex conjugate pole pair is this, right? Is this one. And this is the one that we know how to do the plots, right? Is for this. So we need one of these to be omega n squared divided by this. So let's go back over here and let's just start with that. Let's start with that. We know we need this to be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, which it's already in that form in the denominator, right? We just need to have this omega n squared term, which is a constant, in the numerator, which we can totally do. So let's just, if we look at this, if we just took this numerator and we split it off to a separate term, and then numerator of this fraction then is 1 over, and then we have the s squared, the denominator still. So we have 1 in the numerator. If we want the numerator to be omega n squared, we could just plop an omega n squared in the numerator, but we got to divide by omega n squared somewhere, right? So let's make that division by omega n squared out here in the constant term, because we must do that. And we need to have our first order numerator in the form of tau s plus 1, right? So going back over here, our first order 0, so our transfer functions look like this, should be in the form tau s plus 1. And so we need that to be the case. And if tau s, if we're going to get tau s plus 1 there, we might need to factor something out of the numerator to make that happen. We have to essentially divide this whole term by k over m, right? Because this term has to be 1. We got to make this term 1. So we have to divide this whole thing by k over m, which means that we have to multiply somewhere in this transfer function by k over m. Because if we're going to divide by it, we have to multiply by it elsewhere. So that means that if we're going to divide by k over m to get this, we need to multiply by k over m elsewhere. And we're going to collect all those constants in that front term, all those constants that we're factoring out. So we factored out a k over m. So if I look back over here, we factored out k over m. And then this term that was left is by definition what tau is. We already found out what tau is. So we'll just write it as tau. And we have it. I was going to go through all of the process very explicitly and whatnot, but I think it would be more useful to look at the graphs. So we just did it all by looking at where we needed to go and what we needed to factor out to get there, and we stuck all that stuff in this first term. So this all became a constant term. This became tau s plus 1, a first order 0, and this became the long expression there, which is just the second order conjugate pole pair. So we know how to do all of these Bode plots, magnitude Bode plots, separately, and we just need to add them. So okay, so we're ready to go now. We're ready. Let's first compute our break frequencies, which are very important. Remember the break frequency for the first order systems, for the real 0, those always occur at 1 over tau. If we go back to our Bode plots, we talked about how that was here. The break frequency is at 1 over tau. So 1 over tau And if you compute that, that's 51. We already computed tau, so it's 51. If you compute the second break frequency, which is associated with the conjugate pole pair, right? That's going to be at the natural frequency, which we already computed. Omega n is equal to 20.4. So we know the two break frequencies, so I stuck them on here. I'm not going to be too worried if you guys aren't super comfortable sketching these things without, well, you should be able to use graph paper to sketch them at least. You should be able to use graph paper to sketch them. I will, on an exam, likely give you axes so that you can just draw on them. But I just sort of sketched out. This is how you would sketch them. So you would do 0 dB to plus 40 dB. We don't really know where it's going to be yet. So we do know it's going to go down eventually. We got that second order denominator. And we might have some going up because it's got this 0 in it. And we've got the phase going from plus 180 degrees to minus 180 degrees. And then we have decades marked out here. So 1, 10, 100, 1,000, 10,000. Okay? Because it's logarithmic omega. And we just need to sketch each of them separately, and then we'll combine them. Okay? So, the first thing to know, oh yeah, I forgot to mention this. Let's plug in, do you guys remember what, so K was equal to m omega n squared, right? Remember that from way up here? K is equal to m omega n squared. Actually, K over m is just omega n squared. So if you look up here, K over m is omega n squared, and it's divided by omega n squared. So what is this equal to? 1. Sweet. Guess how you draw 1 on a, well, you notice that it has no effect on the rest of this. Just multiply by 1. You can just take this term away. So how many dB is 1? 0. 0 dB, but it was a good guess. 0 dB. So what happens when you add 0 to everything? Nothing happens. So we don't have to even sketch that part. Whew. That helped. I mean, it wasn't that hard to sketch. It was constant anyways. But all right. And it also adds no phase as well. So we have tau s plus 1. Let's do that one first. So our break frequency is 51. So that happens out here. So I just drew in omega 1 equal 51. That's our break frequency. What is the magnitude below the break frequency in our straight line approximation? I will use green for this one. What is it all the way up to the break frequency in the straight line approximation? We're looking at this situation here, right? So it's 0 dB, and at the break frequency, it takes a dive at negative 20 dB per decade, right? So, sketch 0 dB. Well, I'll sketch it just below so you can see it. 0 dB all the way up to the first break frequency. And then we're going to go down at negative 20 dB per decade. So 1 decade later, we're at negative 20. The next decade later, we're at negative 40. So something like that. And the slope of that line is, oops. Slope of that line is negative 20.
What is that ending at negative 40 or
So, and so I said, okay, it's from here down to negative 40 is 2, so it's 40 dB. If it's going at negative 20 dB per decade, it should take 2 decades to get to negative 40, right? So that's approximately 2 decades, so 1 decade, 2 decades, approximately 2 decades later. I'm a little off, but does that make sense? So decade is a factor of 10, right? So a factor of 10 on this scale is just the same location 1 tick over. So you go 1 decade, you go, these vertical lines are spaced out per decade, so you can just move over 1 increment. Okay, so there's that. We could do the rounding. We do know that there is this this rounding that occurs, right? But let's wait for the rounding. Well, no, we won't. We'll do the little rounding. It's, you know, it gets to like -3 dB. That was a very terrible job at rounding. That was very not round. But something like that. That wasn't so bad. Okay. Oh crap! What did I do wrong? I did something completely wrong. What did I do? It was positive. You guys didn't catch me. God, I did all of that, and you guys didn't catch me. I know. That sucks. So we have a 0. So it's supposed to go plus 20 dB per decade.
I'm a real 0. I'm kind of confused how you're picking these. So like we have a real 0, and we have a conjugate pole, right?
Yes. So there's a real 0. So a real 0 looks like this one, right? And we have a conjugate pole pair, which if we go over here, looks like this one.
Now why is it that one as opposed to any of the 3 there?
Well, so these lower ones are phase. The upper ones are magnitude. So these two go together. They both are for the conjugate pole pair. These two go together. They're both for the conjugate 0 pair. We have a conjugate pole pair, so we're working on this left-hand side here. In just a moment.
Right, left was conjugate pole?
Yep. So we've got a conjugate pole pair. We better sketch as well. So I'll use blue for that. So blue, so the break frequency is omega 2. We already put it on the graph, so it's 0 dB up to there, right? And our straight line approximation. And then what happens there? Well, it goes negative at -40 dB per decade, right? So in 1 decade, which is about here, it's a -40 dB. Oh wait, no. This is 1 decade. Approximately. Somewhere right there. About there. All right.
So the blue line is what? Sorry.
The blue line is for the complex conjugate pole pair. So if I did a little legend here, I would do green line. Ooh, I know. I have this. Watch this. I'm gonna do green line. It's for this one. Yeah, like that. And blue line is for that one. Yeah. All right. So we've got those two. We don't have yet that, so we have the straight line approximation, but we have to take into account that zeta is equal to 0.2, right? So we come back here, we have to choose our zeta. What's our zeta? 0.2. That corresponds to, we don't have that. It's between the blue and the red. So the blue and the orange. So it's like somewhere right here. It goes up to like maybe somewhere like around 10 dB. So let's come back here and we'll make this thing have a little hump here. So we'll say it goes up and then down. All right. So we have our magnitude sketch. Now we need to combine them by adding them. Okay? And all we need to do for that, we'll use purple. Oh, watch this. Purple is this. Wow. That's magic. Okay, so purple, what happens? What's 0 plus 0? 0, 0, 0. Oh, we got to start going up. Here, I'm drawing them right next to each other just so you can see them. And down. Okay. And then we're following this. And then we get to sum these things now. And so what happens when you sum a line that's going at negative 40, slope of negative 40, with a line that's going at a slope of negative 20? Or of positive 20? Yeah, it starts to go at negative 20. So it's going to be, you know, from there. So negative 20 dB is going to be like here. And that's about a decade. So yeah, something like that. So this is our slope, and this one has a slope of negative 20. So we've sketched it. We've done it. It's amazing. The phase is also here. We have to do the phase. It'll just be a minute though. So the phase for the 0 starts at 0 and goes to plus 90, right? So we started off at, use green, started off at 0, 0, 0, 0, 0, and then it's going to go up to plus 90, and so if we go way out here, we're going to be at plus 90, and we've got to talk about how it transitions, right? Remember, you go to the break frequency, so that's omega 1 for the 0, and we put a dot right on 45 degrees and the break frequency, right? Then we go down a decade, which would be about here, and we know it's got to be at 0, down a decade. And we go up a decade, which is about here, and you know it has to be at positive 90. And then we're going to draw a straight line approximation between those, and then we can fill in the rest of these straight lines. So there's that one. The conjugate pole pair has these phase plots. So let's draw the straight line from 0 to the break frequency, and then it drops down to 180. We've got this, you know, it's really more like 0.3 or 0.2 zeta, so it's, you know, it's actually going to have a pretty decent curvature to it. So we'll put it in as best we can. It's hard to do this one. We're going to kind of punt on how well we'll do it. So with blue, so it's 0, 0, 0. Our totally straight line approximation is going to be 0, 0, 0, all the way up to the break frequency, which for the complex pole pair is omega 2, which is this first one here. And we drop down to negative 180, right? And then we're straight again. In reality, it's probably more like that, right? So now we just need to add them. So there's our purple. And 0 plus 0 is 0 since today. And then it's going to start to drop a little bit with this curvature, and then it's going to start to come up, and it's really hard to say who's winning at this point. And then definitely at some point, so it's probably going to come up a little bit here. Definitely at some point it's going to drop back down. And what is it going to end up at?
Negative 90.
It's going to end up at negative 90. because plus 90 and negative 90, or negative 180 equals negative 90. So that's approximately what we get out. So we learned how to do all the sketches. Yes?
So omega 1 is the break frequency for the zeros?
Yep.
And omega 2 is the break frequency for the poles?
Yes.
Okay.
And that's because we just defined them to be so.
Okay.
We could have defined them otherwise, but we just wrote them right like that here. So.
Yeah.
You scroll down slightly.
Yes.
Sweet, thank you.
All right. Do you guys feel so excited about these?
This is kind of cool. Depends how complicated this is.
Yeah. I mean, if you guys can do an example around this degree of difficulty, you'll be totally fine on the exam. This is about the degree of difficulty that I would expect you to be able to do on an exam. So, I mean, it's not. And also, here's the other thing: the sketches. I want you to try hard on them, but recognize that I do not care if it's perfect. So, you know, just try to make sure that asymptotically it's correct, and do the best you can. I don't expect you to be able to approximate what's going on in here super well. There's a lot happening in there. But you should be able to say, I mean, at any point you can calculate a point on it by just saying, okay, what is 48 degrees plus negative 180? Well, there's a point right there. So you should be able to put some points on there if you need to and sketch. All right. Yeah, Victor.
When you're doing the magnitude, right? How do you know that you're supposed to go down? I mean, the first one, the green one, you went up 20.
20.
But where'd you get that 20 from? And then the next one, you went negative 40. Was that from the...
So whenever you have a conjugate pole pair, you're going to be going down by 40 dB per decade.
Okay.
Whenever you have a conjugate zero pair, you're going to be going up 40 dB per decade. Just from those, yeah. And then if you come out to
The ones before.
the ones before, these always end up at 20 dB per decade, negative 20 and positive 20.
All right.
Yeah.
It's supposed to make a
All right, so if there are no more questions on that, I'll stop the recording.
I'm not sure.
Yeah, I'm